Okay, so now let us look at a single linked list based implementation of a stack. So again, as I said earlier, you want to maintain the top of the stack near the head node so that you can accomplish the push and pop operations in big O of one time. Okay, so let us take a scenario. Let us say you have a stack like this. So if this is single linked list, so I said the top of the stack is the data node next to the head node. So this is the top of the stack. So 7 is in the top of the stack. Then below it you have 5 and 10. So that means you really push 10 as the first element to the stack, and then you pushed 5 and then you push 7. So now I want to push one more element to the stack, say 9. So how are we going to accomplish this? That's what we're going to see. So in order to do that, let us look at the code. So we want to say insert at index, where insert index is really 0. You want to insert at index 0 and then the data. So these are the two arguments. So you as usual start with 2 pointers, the current node pointer and the previous node pointer. So the current node pointer is pointing to the node next to the head node, and the previous node pointing is storing the address of the head node, and index is 0. Now current node pointer, if it is not null, so that means the stack has at least one element in it. If there's no element in it, then you don't go inside the while loop, you just add the new node to the stack. So if there's at least one element in it, like in this case, yes, so we'll get inside the loop and check if index equals insert index. Index is 0, insert index is also 0, so you just break out of the loop. So why I really show this code is because this is the code that we use for a single linked list based implementation of a list ADT. So I'm showing that we can reuse the same code for the implementing a stack ADT and just pass insert index to be 0 when you really want to implement the push operations. So the way you can do that is you write a function push and then pass the data as the argument for the push function, and inside the push function call the insert at index function on the single linked list object. So and then pass insert index as 0 and then the data that you want to push. So what we are doing here is creating a new node and setting the new node pointer to store the address of the new node and set the data for that node. Now these two are the important statement that you have to do. So the new node's next node pointer equals set to the current node pointer. So the new node's next node pointer. So this is a new node that we created. Its next node pointer value is set to be the value of current node pointer. So current node pointer is pointing to this node 9 at address 900. So that's the value you are setting it for the next node pointer in the new node here. And then the head node's next node pointer is set to this new node pointer. So and we have the previous node pointer also showing the address of the head node. So previous node pointer arrow set next node pointer will be this new node pointer. So that way, if this is a linked list before this push operation, you are trying to create a new node and make its next node pointer to point to this current node, and the head node's next node pointer will now point to this new node. So you are breaking this link and setting up the two links like this. Okay, so that's the push operation. So let us now look at the pop operation, which is similar to deleting an element at index 0. So this is say the stack currently that we have, and you want to do a pop. So that means you want to remove the topmost element out of the stack. So again, the top of the stack is the node next to the head node. So this is a data node that you really want to pop out, and the data 9. So after the pop operation from the head node, you should be able to visit this node, which is now in the top of the stack, and so on. Okay. Alright, so how we accomplish this is, now again this delete operation, in the case of a single linked list, we maintained for the list ADT 3 pointers, the current node pointer and previous node pointer as usual, and the next node pointer also storing the address of the head node, and index is 0. Now current node pointer is not null. If there's at least one node in the stack, yes, current node pointer is not going to be null. So get inside the loop and index equals delete index, which is 0. So once it is the case, then what you do is store the address of the next node. So current node pointer arrow get next node pointer. So store the address of the current node's next node. So this is where the current node pointer is pointing to at address 500. So current node's next node pointer is 900, which is the address of the next data node. So you store this as the value of next node pointer. So next node pointer equals current node pointer arrow get next node pointer. So current node's next node pointer is stored as the value of next node pointer. And then you break from the loop. Then the previous node pointer, which is the value of the head pointer, so in the address of the head node. So basically the head node's next node set next node pointer to be a next node pointer. So that means the head node's next node pointer is currently 500 pointing to this first data node. Set its next node pointer to the address to the value 900, which is the address of the next data node. So that means setting that you are kind of isolating this first data node, so you cannot visit it at all. Even though this link is there, there's no use of this link because you cannot visit this node first of all. So from the head node, you'll be able to go now to this data node, which is not the top of the stack. So that is the delete operation. So in the case of so again a single linked list, the top of the stack is the data node next to a head node, and the bottom of the stack is the last data node in the linked list. Now in the next video, we are going to look at a double linked list based implementation of a stack. And in that case, we will maintain the data node next previous to, that is the previous node to the tail node, as the top of the stack. So in that case, the data node that is next node to the head node will be the bottom of the stack. Now you can do this vice versa also. So with a double linked list, it doesn't matter. Both ways you can accomplish big O of one time. Whereas in a single linked list, since you can traverse only in one direction, you want to be able to push and pop in constant time, so you maintain the data node next to a head node as the top of the stack. Okay, so we'll stop the video with this.